So this material that we're doing today is from week 8. Okay, so if you're following along the syllabus, this is actually going with week 8 stuff, which means if you're looking at the syllabus for practice problems, look at week 8, okay, because that's where we are in the syllabus. Today we're going to do reactions in aqueous solutions and solution stoichiometry, and then we'll get to complete net ionic equations next time. Okay, so if you don't have your solubility rules out, please take a second and find them. You can also open your books, page 108. So solubility rules handout that I gave you. Again, in this semester, we're using the word soluble and insoluble, but just so you know, right, solubility is not this black and white kind of thing. There's a very large gray area. In some ends, it's so gray that it looks black, and in some ends, it's so not gray that it looks white. Right? But that's technically an equilibrium condition, which we'll deal with in great detail next semester. But right now, we're either calling it yes or no. All right, so take a second. Let's just shout out our answer. Decide if these are soluble or insoluble. Potassium chloride, soluble or insoluble? Soluble, right? So all chlorides are soluble with the exception of a couple. What about barium sulfate, soluble or insoluble? Insoluble, right? And then copper 2 acetate, soluble or insoluble? Soluble. Good job. Okay, now let's just review our displacement reactions. We've got single displacement and double displacement, right? We learned these several weeks ago. Single displacement is when you've got a metal and an ionic compound. This is the experiment you did in lab last week, right? You used silver nitrate, though, not silver sulfate. That should be Ag2SO4, just realized that. But anyway, your copper metal, you put in, you got silver metal, and then you got the copper ion, remember it was blue. Double displacement is when you've got 2 ionic compounds, right? The cations and the anions switch. Right, so this is the exact experiment you did last week. Silver nitrate was the solution you used, right? And you saw this exact phenomenon. Okay, now we've already used this word, but let's refresh our memory, right? A precipitate is an insoluble product that is produced during a displacement reaction. So you already know how to do a double displacement reaction, right? This is something we've done forever ago. Now what you're going to do is you're going to look at the products of that double displacement reaction, and then you're going to look at to see, is the product soluble or is the product insoluble, okay? Because from here on out, in this whole little unit, we're doing reactions between 2 solutions, right? So we've got a solute dissolved in a solvent. That's solution number 1. We've got another solute dissolved in a solvent. That's solution number 2. We're mixing them together, so that will be a double displacement reaction, okay? And then we're either going to get no product, in other words, they'll just mix and there will be no reaction, or we'll get a precipitate, which will be an insoluble product, okay? So that's what we're going to be looking at here, and we're going to be doing some stoichiometry. So from here on out, you need to write the state of matter in all of your equations. And the ones that get people in most trouble are when to use liquid and when to use AQ. Okay? Oh, and S gets people in trouble too. Okay, what does S stand for? Solid. I have so many people who tell me S stands for soluble. And so they'll look at their solubility rules and they'll say it's soluble, and so they'll put S next to it. Okay, that's not what it means. S stands for solid. So you put S next to a precipitate. Okay, so if you're looking at your solubility rules and you see that something is insoluble, that's when you put S, because insoluble means solid. Okay, so please make sure you understand that S stands for solid. It does not stand for soluble. If something is insoluble, it's a precipitate. That means you put S next to it. If something is a liquid, pure liquid, that would be the only time you put L. Okay, so for instance, H2O, L, or Hg, mercury, is a liquid, L, okay? Do not use L for a solution, because a solution is not a pure liquid. A solution is a solute dissolved in a solvent, okay? So if you've got a solution, for instance, NaCl solution, you would not use L, you would use AQ, okay? AQ means aqueous, L means liquid, and then gas. Nobody really worries about gas. I think everybody understands what gas is. But don't confuse liquid and AQ, okay? Liquid is when you have a pure liquid. So CH3, OHL, right? That'll be liquid. AQ would be KBr AQ. Okay, so if you've got a solution, it's AQ. So again, if something is soluble, if it exists as a solution, we put AQ. If something is a precipitate, we use S, and we do not use L for a solution. We only use L if we have a pure liquid, not if we have a solution. Does everyone understand the difference between these subscripts? Which one to use when? All right, so let's take a second and practice. Give me two balanced equations. You're going to need your solubility rules until you learn them. Write a balanced equation for the reaction that occurs when solutions of iron 3 sulfate and lithium hydroxide are mixed. So for your reactants, you don't need to look up the solubility of your reactants, okay, because your reactants are both solutions. So they're both going to be AQ. Okay, you don't need to look up the solubility of your reactants because the problem states they're solutions. So that means AQ, AQ. All you need to look up is the solubility of the products. Okay, is it AQ or is it S? And then secondly, will a precipitate form when solutions of calcium nitrate and potassium hydroxide are mixed? Write a balanced equation. Again, you don't need to look up the solubility of your reactants because the problem tells you that it is solutions. That means that it is soluble. Okay? All you need to look up is the solubility of your products. So I'm going to pause the recording, give you a second to do that. Let's see the answer here. So in part A, are you going to get a precipitate? Yes or no? Yes, you do get a precipitate. The precipitate is what? Iron 3 hydroxide. So you don't have to look up the solubility of your reactants because the reactants are told that they are solutions. That means that they have the subscript AQ. Okay, so you never need to look up the solubility of your reactants because the problem says solutions. Therefore, you know that they're soluble. All you need to do is figure out what your products are, do your double displacement, and then look to see what the solubility of your products is. Okay, so if you look up hydroxides, hydroxide is listed under insoluble compounds. Most metal hydroxides and oxides, with the exception of the alkali metals, so that's group 1, barium hydroxide, strontium hydroxide. So iron 3 is not one of the exceptions, so it is insoluble. If it's insoluble, that means it's a precipitate, so that sits on the bottom of your beaker as a solid, right? That S stands for solid. You look up lithium sulfate, sulfates, let's see, salts of sulfate are all soluble except these ones. Lithium's not listed as an exception, so it's AQ. Do we agree on this one? These are all double displacements, yes. If you had a metal and a solution like what we did in lab last week, that would be single displacement. Are you going to get a precipitate in B? Yes or no? Precipitate in B. Yes, you do. Precipitate is calcium hydroxide. Because you don't have to look up your two reactants because they are both solutions. But you do have to look up your products. All nitrates are soluble, so AQ. When you look at your hydroxides, again, it says most metal hydroxides are insoluble except alkali metals, that's group 1. Calcium's not in group 1, calcium's in group 2. Barium and strontium. No, calcium is not barium, calcium is not strontium. So it is insoluble, so you have an S for precipitate. So both of these reactions produce precipitates. Do we understand how to do this? We've been running double displacement reactions for a long time now, right? So the only new part is looking up the state of matter of your products, okay? And it's either going to be S or AQ, unless you see bubbles forming, right? Then it'd be gas. All right. Vast majority of the ones you'll see are going to be solids or AQ, right? And if you see bubbles, that obviously means gas. Okay, now let me ask you a question. Can you just look at a sample and see if there are ions in it, right? If I just held up my water here and I'm like, okay, guys, are there ions dissolved in this? Can you tell just by observation? I mean, you could tell if there's copper too in it because it'd be blue, right? But otherwise, could you just look at it and be like, is there any lead in there? You can't do that. You can't see those ions. It's not possible. So the way that you can tell if your substance and if your sample contains ions is by testing, okay? So for instance, let's look at the solubility rules. What's something that we could add to our water? Let's get a sample from the water here. What's something that we could add to our water sample to see if it contains lead? Lead ion is not something you want to be ingesting. So what's something that we could add? There are a lot of choices here to see if our water contains lead. Lots and lots of choices. Someone give me one. Chloride would work, yep, because it's under all salts of chloride are soluble except lead 2. What else could we add? Well, by that same logic, we could add chloride, we could add bromide, we could add iodide, right? And it doesn't matter what the cation is. It could be sodium chloride, it could be potassium chloride, it could be, you know, lithium chloride, right? We're not interested in the cation, we're interested in the anion. What other things could we add to see if our water contains lead? We could add sulfate, right? All sulfates are soluble except lead 2 is listed as an exception. What else could we do? Fluoride, right? All fluorides are soluble except these ones. And then notice under the insoluble compounds, right? Any of those would work too, right? Because lead is going to be insoluble with carbonate, phosphate, oxalate, chromate, sulfide, etc., right? So any one of those would produce a precipitate. So we add our sample, we add our anion of interest, right? If we get a precipitate, then our water has lead in it, right? If we don't get a precipitate, then our water doesn't. Or we just have it at such a low concentration, such a very low concentration that we were making a precipitate that was not able to be detected by our eyes, right? So lead 2 iodide is a yellow precipitate, bright yellow, mustard yellow. So if you added that iodide ion, you get a precipitate, you know, hey, I got lead in my water. I should probably be calling the city, right? That's not something I want to be drinking. So you can't tell whether or not an ion is in a sample just by observation, right? You have to test it. And in a couple weeks, you're going to be doing a lab where I think that's the premise of the lab. It's either you're identifying the ions that are in the water or you're identifying the concentration. I can't remember which one it is. Maybe both. Okay, so now we're going to get into some stoichiometry involving solutions. Because if we're dealing with quantities, right, molarities and masses and all that good stuff, we can do calculations to figure out molarity. We can do calculations to figure out how much precipitate I could form. We can do a whole lot of neat calculations using stoichiometry and with the solution chem spin. Now, the big difference between solution stoichiometry and quote-unquote regular stoichiometry is that stoichiometry, when you're dealing with it in the solutions, is going to depend on what your information you're given and what information you're looking for, right? In regular stoichiometry, quote-unquote, step 1 is always grams to moles. Step 2 is always mole ratio. Step 3 is always moles back to grams, right? That's the procedure. It's the straight-out procedure, always. Boom, boom, boom. But with solution chemistry, okay, your steps are going to be a result of what information you're given and what information you're looking for. So just be careful, okay? Be careful. A lot of students either love solution chemistry because it's so different each time and, you know, you're always thinking differently, or they hate it because every problem's different and you have to think through it every time, okay? So depending on how you approach it, right, you're either going to love it or hate it probably. I hope you're going to be on the love it side, not on the hate it side, but we'll see. Here are the general steps. Now I say general, again, because solution stoichiometry is going to vary based on the information you're given. But number 1, you always have to find a way to get number of moles. Find a way to get number of moles. I don't care how you get number of moles, but you're going to have to get it somehow. So either you're going to multiply molarity by volume, right? So if I say you've got 15 milliliters of a 5 molar solution, that would give you number of moles, right? Molarity times volume. If molarity is moles over liters, then moles is molarity times liters, right? Make sure this volume is liters, okay, not milliliters. Or let's pretend that it's a precipitate. You're using a precipitate to calculate backwards. Well, if it's a precipitate, that would be a mass in grams, right? You could convert grams to moles just using molar mass. So those are the most two common ways to get number of moles. But in step one, somehow you need to find a way to get number of moles. Doesn't matter how you get it, find a way to get number of moles. In step two, we're going to multiply by the mole ratio. So step two here is no different than step two of regular stoichiometry. Okay, that step's the same. So you just need to make sure you have a balanced equation, right? And those mole ratios come from the coefficients of the balanced equation. And then step three, you're going to convert based on what your problem asks you for. Okay, so if it's asking you, what volume do you need? Well, you can use the molarity and the number of moles. Or if you're looking for mass of the precipitate that could form, right? You convert moles to grams. So it just depends. Step three and step one are the two variables. These are going to change based on the information you're given and the information you're looking for. So this is why I say there's really no step one, step two, step three procedure that's going to be the same, because the information that you're given and the information you're looking for determine your steps. Does this make sense? We're going to do several examples. I'm going to show you an example, then I'm going to give you time to do some guided practice, and then we'll go over. Does anyone need me to leave it here longer? Okay, let's do this one together. When 50 milliliters of a 0.115 molar silver nitrate solution reacts with a 0.125 molar calcium bromide solution, how many milliliters of the calcium bromide solution must be used to achieve a full reaction? So in other words, I want my two solutions to react with each other completely. I want solution number one to completely consume solution number two. Okay, that's what this problem is asking. So how much of the second solution do I need to use in order to completely use up solution number one? I'm mixing the two together, right? So I take solution number one and I dump it, solution number two and I dump it. How much of number two do I need to dump in order to completely consume solution number one? Does everyone understand what the problem is asking for? When I say to achieve a full reaction, that means to completely consume the other solution. Right, so if you want to think about it, like we haven't talked about acid-base yet, right? But we'll do something similar when we do acid-base. If I've got a base, how much acid should I add to completely neutralize it? Right? That's the question that we'll ask when we do acid-base. We're going to do the same thing here. How much solution number two do I add to completely consume all of solution number one? Well, we all know that eventually I'm going to need coefficients, right? I got to have coefficients, so that means I have to write a balanced equation. So the first thing you have to do is you have to look up, you have to write your products. This is double displacement. Now here, you do get a precipitate, but does that precipitate factor into these calculations in any way? Are you interested in the precipitate at all? Does the problem ask you, what mass of the precipitate will form or anything like that? No. So we're writing this equation and we're balancing it, and it's great to know that that's a precipitate and that's aqueous, but the state of matter here is not going to have any influence on my calculations. Okay, so again, it's all about organizing the information. This is why I recommend that you list what you know and what you're looking for underneath it. And I also recommend that you go ahead and convert milliliters to liters in step one, okay? If you forget to convert milliliters to liters, when you multiply molarity times volume, you will not get moles, you will get millimoles, okay? So you want moles, not millimoles. So make sure that you convert milliliters to liters. And I go ahead and do that right out of the gate. That way you don't forget to do it. Okay? The problem tells me that I've got 50 milliliters of AgNO3 and its molarity is 0.115 molar. That's what the problem told me. And it's asking me how much of the calcium bromide solution should I add to completely consume it. I know its molarity. I just need to know what volume of it I should add. Okay? Does everyone understand what we're looking for? What? Yes, we're looking for the volume. So our final step, our step 3, is going to be based on what we're looking for here, right? So step 1 is always get moles. Find a way to get moles and get it. We don't know any masses here, right? It's like it said 5 grams. So we can't convert grams to moles. But we do have a molarity and a volume, right? Molarity times volume is always going to give you number of moles. If moles over liters is molarity, then moles is molarity times liters. So step 1 is always going to give you moles somehow. Find a way to get moles. The 2 most common ways you get moles is either converting grams to moles, which we don't have here, or multiply molarity times volume. So those are the 2 things that we know. We know the volume, we know the molarity. If I multiply those 2 together, right, moles per liter times liters, well, that cancels out liters. So that gives me moles as my unit. So that's 5.75 times 10 to the negative 3rd moles. Does everybody understand how we did step 1? Molarity times volume gives number of moles. So find a way, any way, to get moles in step 1. Everybody good on step 1? We multiply molarity times volume. Okay, step 2 is the mole ratio. So that step's the same as in regular stoichiometry, right? It's the mole ratio from the balanced equation. So I'm interested in turning my AgNO3 into CaBr2, right? That's why AgNO3 is on the bottom and calcium bromide is on the top, so that AgNO3 cancels and I'm left with calcium bromide. Right? The mole ratio is 1 to 2. So I take 5.75 times 10 to the negative 3rd, multiply by 1, and divide by 2. So step 2 here is the same as step 2 of regular stoichiometry, quote unquote. This part's no different than the stoichiometry you've already been doing. Make sense? Now we convert it based on what the problem asks. We now know the number of moles of calcium bromide, and we know the molarity, right? And the problem asks for volume. So you just plug it in, regular old arithmetic, right? If molarity is equal to moles over liters, and we know its molarity is 0.125, 0.125 is equal to, and we just solved for moles in the previous step, so 2.88 times 10 to the negative 3rd over x, right? So we're just doing regular old algebra. So 0.125x is equal to 2.88 times 10 to the negative 3rd. So x is 2.88 times 10 to the negative 3rd divided by 0.125. Now that'll give you a unit in liters, right? Because molarity is in liter, I mean volume is in liters in molarity. So that'll give you 0.0230. My unit is going to be liters because molarity has the volume in liters. Can you measure out 0.02 liters easily? No way, no way, right? But you can convert that to milliliters, which is something you can measure out quite easily. And we have 3 Sig Figs because we have 3 Sig Figs in all 3 of our measurements to begin with. Okay. So I want to show you where this comes from. So I see a lot of students memorizing, okay, to get volume, that's moles divided by molarity. You don't need to memorize formulas, right? If you know this one formula, then you can plug into it and do the arithmetic. Okay, so you don't need to memorize formulas. So long as you know this one parent formula, if you know any one of those other 2 of those variables, you can solve for the 3rd one, just basic algebra. Okay, so that's why I want to show you where this comes from. Okay. Does this make sense? Makes sense, makes sense. Ready to try one for yourself? Okay, do this one. How many milliliters of a 0.1 molar silver nitrate solution are needed to react completely with 25 milliliters of a 0.4 molar calcium chloride solution? So this is the exact same premise as the previous problem, right? Here's a solution with a known concentration. How much of it do I need to add to my second solution in order to completely consume it all? I will give you a few minutes to work on this one. So we need to figure out Sig Figs. Our final answer will have 3 significant figures, right? Because all 3 of these values have 3 Sig Figs. 3, 3, 3. So in terms of Sig Figs, our final answer needs 3 as well. So first thing we need to balance the equation. We do have a precipitate, but does that factor into our stoichiometry in any way? Nope, 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 it doesn't. Because I'm trying to find out how many milliliters of this solution I need to add in order to consume all 25 milliliters of this solution. If this is its molarity and this is its molarity, right? You can't just assume 25 and 25, right? You can't make that assumption because they have different numbers, they have different molarities, and there's a different mole ratio, right? So it's not just a 1-to-1. You can't say, oh, 25 and 25. That doesn't work. So these have different molarities, and there's a different mole ratio. Mole ratio is 2 to 1. So the first thing we did is calculate number of moles, right? So volume times molarity is all this is, right? Because this is 25 milliliters. That's the same thing as 0.025 liters. So volume times molarity. So liters cancels. That's how I get moles. So 0.01. Do we agree on step 1? Do we agree on step 1? I mean, there's no rounding to do here. You could put 0, 0, 0 at the end, but in terms of rounding, there's no rounding to do. Step 2 is the mole ratio, right? So we have 0.01 moles of calcium chloride. It goes on the bottom, so I'm trying to get rid of it. Mole ratio is 1 to 2. That's why there's a 2 on top and a 1 on bottom, because I'm trying to convert to moles of AgNO3. So I take 0.1, 0.1 multiplied by 2. That gives me moles of calcium chloride. And now I know number of moles of calcium chloride, I can figure out volume, right? Because if I know the molarity and I know the number of moles, I just plug into molarity equals moles over liters and solve for liters, right? So when you do 0.02 divided by 0.1, that gives you 0.2 liters, which you could not measure out effectively. But you could measure out 200 milliliters very effectively. And it would be 200 with a decimal place, right? Because this needs to have 3 significant figures. So if you forget the decimal place, it only has 1 sig fig. Right? So make sure that you include the decimal place to tell the reader that this has 3 significant figures, not just 1. Questions on this problem? Questions, questions, questions. If you made a mistake, do you see where you made it? Anyone need me to leave it here longer? Okay. What about this one? See if you can figure this one out. How many grams of magnesium metal are needed to fully react with 20 milliliters of a 0.150 molar copper-2 iodine solution? Think about what kind of reaction that is. So this problem was a little bit different, right? First of all, was it a double displacement reaction like the other ones? No, this wasn't double displacement. What kind of reaction was this? This was single displacement, right? How did you know? because you have metal and a solution, right? So the metal becomes the new cation that gets together with the anion, and the cation becomes the new metal. Right? So this is like what you did last week in lab. You did a double displacement reaction last week in lab, right? Metal becomes the cation, which gets together with the anion, and the cation becomes the new metal. So that's the balanced equation. It would look similar to what your precipitate looked like last week, except instead of being a grayish color, it would be brown, right? Copper metal would be kind of a brownish color. Okay, so now we're looking for number of grams. So if I have this solution with this molarity and this volume, how many grams of the solid should I add to that solution to completely consume each other up? Right? That's what I'm asking here. So step one is still going to be the same. Right? Number of moles is obtained by volume times molarity. Right? If moles over liters is molarity, then moles is molarity times liters. So volume in liters times molarity. Liters cancels, that gives me moles. Okay. So step one is still the same as what we did in the previous problems. Step two is the mole ratio. Mole ratio here is 1 to 1. Okay. So my number doesn't change, but my units do. So even if the number isn't changing in the mole ratio step, you need to show this step so that you communicate to me that you know how to get from one unit to the other. Okay. Even though the number doesn't change, and I know it's extra writing, remember the whole point of a quiz or the whole point of a test is to tell me that you know what you're doing, right? So by showing me this step, that tells me, hey, I know how to convert from this unit to the other unit. Okay? So even if the number's not changing, I still need to know how you got from one unit to the other. And now we've got moles. The problem asks how many grams. So what do I use there? Just the molar mass, right? Molar mass is 24.312 grams per mole. Rounding my final answer to 3 significant figures, I got 0.0729 grams. Did you? Okay, this is why I say solution stoichiometry is going to vary depending on what you're given and what you're looking for, right? Step one and step two were the same in this problem as it was in the other problems, but step three differed because this was single displacement, right? So I was looking for grams. If I'd gone the other way, maybe I gave you mass here and I gave you the molarity and I wanted to know what volume this needs to be, right? You could do that. Or maybe I gave you mass here and I want to know, I don't know, what molarity is here. Or hey, maybe I give you this information and I want to know what mass of the precipitate, right? You have to look at what you're looking for in the problem. Okay, now you can do it all as one big long calculation, just like you can do regular stoichiometry as one big long calculation. You can do solution stoichiometry as one long calculation, but I only recommend doing it when you've got it down really well. Okay, so this isn't the same problem. I don't know why it says that. So this should be a different problem. And this should say solid right there. I don't know why it says AQ. So you've got your sulfuric acid, you've got solid sodium hydroxide. How much solid sodium hydroxide should you add to consume all of this sulfuric acid? So what you're doing here, here's step one, right? Multiplying number of moles. There's step two, the mole ratio, and then there's 3 converting to grams. Let's do this problem together. When 200 milliliters of a solution of calcium nitrate, and its concentration is unknown, we don't know what its concentration is, reacts with excess magnesium sulfate, 2.31 grams of the precipitate are produced. What is the molarity of the unknown solution? So again, this is still solution stoichiometry, but we're looking for a different variable this time. $200 milliliters of calcium nitrate of unknown concentration. Someone was lazy and didn't write the label. doesn't have the molarity on it, reacts with excess magnesium sulfate. Excess means this is not limiting reagent kind of problem yet, right? We'll get to that next time. 2.31 grams of the precipitate are produced. What's the molarity of the unknown? So let's do this one together. First thing you need is a balanced equation. You need to identify which substance is the precipitate, because I didn't tell you which substance is the precipitate. I just told you that there is a precipitate and its mass is 2.31 grams. But I didn't tell you its identity, right? So this is double displacement because you've got two solutions. And we're producing magnesium nitrate and calcium sulfate. I have to consult my solubility rules in order to figure out which one of these is the precipitate. Right? Magnesium nitrate is soluble, calcium sulfate is insoluble. That makes it my precipitate. So the problem says 2.31 grams of the precipitate, that's referring to this. And we know the volume here, but we don't know the molarity. Okay, so that's the information that we're given in the problem. Is everyone with me on how we set this one up? This time, we're not trying to find out what volume I should add. We're trying to figure out what's its molarity. So whoever prepped this solution forgot to write its molarity on the bottle. Whoops. When I combine these two things together, here's the mass of the precipitate that I make. Can I solve for molarity knowing that mass of precipitate? Is that something I can do? Yeah, that's something I can do, right? So first thing I'm going to do is convert grams to moles because I know the mass of that precipitate. I just converted to moles. Here's the first example we've done today where it wasn't an even number with no rounding. Right, this one does involve some rounding finally. So we're converting grams to moles because that's the mass of the precipitate. Everybody good on step one? Converting grams to moles. Everyone good on why we're doing it this way? Does this make sense? Why we're doing it this way? Okay. Now we're going to multiply by the mole ratio. Mole ratio is 1 to 1, right? Coefficient. There are no coefficients, which means coefficient is 1. So the number doesn't change, but the units do. Again, even if the number isn't changing and you're only changing units, please show me this step so that you can tell me that you understand how to change units. Okay? So that communicates to me that you understand how to go from one unit to the other unit. I know it's extra writing. I know it's kind of a pain to write something out that doesn't actually change the number, but it does change the units, and units are important to us. So I need to know that you understand how to convert. So the mole ratio is 1 to 1. Okay, now in step 3, we're going to do step 3 slightly different, right? Because now we know moles and we know volume. How will we get molarity? What is the formula for molarity? Moles over liters, right? So don't forget to convert milliliters to liters, right? 200 milliliters is 0.0200 liters. 3 Sig Figs in my answer. And don't forget units, right? So either capital M, or you could write out MOL/L, moles per liter. Does this one make sense? Are we starting to pick up on the pattern here? Every problem isn't going to be identical, but they are going to follow a similar theme, right? They're all going to involve a general theme of find moles some way, do a mole to mole conversion, right, with the mole ratios, and then do some sort of conversion involving the molarity equation, or converting grams to moles or moles to grams. Okay, so again, please watch really carefully to what you're given. So we've got enough time to do this one. How many grams of precipitate are produced when 500 milliliters of a 2.85 molar calcium chloride solution reacts with excess potassium carbonate solution. This will be the last one for today. Let's go over this last problem before we're done. Now notice by the wording it says excess potassium carbonate, right? That means that you've got more than you need, in other words. So what does that lead us to conclude that's coming next, right? If we have excess now, we're not looking at limiting reagent in any of these problems, are we? On our next lecture, right, we're going to be considering when you've got information about both reactants. That'll be a limiting reagent type scenario. Okay, so just paving the way for what we're doing next time. So we want to know how many grams of precipitate we could expect if we've got 2.85 molar calcium chloride and an excess potassium carbonate. So first thing we need to do is balance the equation and write it. Figure out which substance is the precipitate, because that's going to make a difference. Calcium carbonate's the precipitate. Potassium chloride is soluble. Now, here's what it looks like if you do it as one big, long calculation. You do not have to do it this way, okay? Again, I repeat, you do not have to do it this way. Only do it this way when you're ready, okay? So here's step one. We're multiplying molarity times volume, right? Volume times molarity. Liters cancel. That gives me moles of calcium chloride. Now we're doing mole ratio, which is 1 to 1, so moles of calcium chloride cancel. I'm left with moles of calcium carbonate. Starting to run out of room, so I just rounded my molar mass to 100, converting moles to grams. I got 143 as my final answer. Did you? 143? Okay, again, please make sure you understand. You do not have to do it as one long calculation until you're comfortable doing it as 3 separate calculations. Okay? If doing it as 3 calculations gives you problems, then it's definitely going to give you problems if you try to smash them all together as one. But if you're done with doing them all separately, and you're like, you know what, I can do them independently, no problems, I can set it up correctly 100% of the time, then you're probably ready to smash them all together and save yourself some writing. Okay? So you multiply straight across and divide up. Any questions on this last one? So next time we'll start talking about limiting reagent, right? All these problems today, we had one substance that we knew information about and excess of the other. Next time we'll talk about what happens when you know information about both reactants or both products. That will be limiting reagents. Okay. Also, don't forget tomorrow being Thursday, lab day. So have a good day, and I'll see you tomorrow.